Hi, this is Jack Jackson. In this video, we're going to talk about advances in number theory and algebra in the 19th century. So, in general, we've seen that the 19th century there's a move towards more abstraction and more rigor. And we saw this in analysis, but it's also true, at least as true, in number theory and algebra as well. So, for example, some things that were accomplished in the 19th century is rigorously defining real numbers, working on the foundations of even just what a real number is. In number theory, there was more work on Fermat's last theorem. First, there was some work on solving some more special cases of that, but uh, there was not a general solution until much later, actually the very end of the 20th century. Wiles finally proved that. There was work on solving polynomial equations by radicals. Okay, if you remember there, by this time we already had basically, linear formula, quadratic formula, cubic formula, quartic formula. So there's work on trying to find a fifth degree formula or more. And we actually found in the 19th century that there was no general method for doing that. Abel proved that first. And then Galois theory allowed us to find out which types of or which equations could be solved by radicals and which ones could not. Then we get the beginnings of abstract algebra, work with groups, rings, and fields. And this is a big area here where we take the ideas of basic algebra, and which is basically generalized arithmetic, and then expand that and abstract that to look at different structures with certain uh, characteristics. Along with that, we have Boolean algebra for logic. Hamilton came up with the quaternions, which help lead to vectors. We have matrices and some early work in linear algebra. So all of these things were going on in this century. So first we'll talk about defining real numbers and the creation of set theory. And I want to lift up two mathematicians, Dedekind and Cantor. Richard Dedekind was born in 1831 and died in 1916 in Germany. He did his doctorate under Gauss at Göttingen. He was a fellow student with Riemann, and he and Riemann started teaching at the same time. And his work really took off after Dirichlet took Gauss's seat, and they collaborated a lot. His early work he did very early work in group theory and ring theory. He worked on the ideal of a ring, and he defined real numbers via Dedekind cuts. George Cantor was born in, that should say, 1845 to 1918. And he was born in Russia, ended up doing a lot of his work in Germany, where he ended up dying. He was taught by Weierstrass, one of the many very famous students that Weierstrass taught. And he is most known for his founding of set theory, his work for cardinalities and infinite numbers. He proved that real numbers are uncountable, but algebraic numbers are countable. So he's talking about this idea of different sizes of infinity, which is a pretty wild concept. There are actually more numbers between 0 and 1, more real numbers, than there are all natural numbers, or even all rational numbers, or even bigger, all algebraic numbers. He worked with trigonometric series, and he defined real numbers as limits of Cauchy sequences of rational numbers. So Dedekind and Cantor had two different approaches to defining real numbers. One thing that's interesting about Cantor and set theory that's really kind of unusual and unique, if you look at most mathematics, it sort of comes along. People make revolutionary breakthroughs, but then then a certain number of things are being looked at by lots of people. We have oftentimes the stage is set and the time is ripe for certain ideas come forth, and sometimes even different people will find those ideas at the same time. For example, calculus was right there ready to be discovered, and Newton and Leibniz found that at the same time. What they did was fantastic and very important work, but it was ready for it. Cantor is a little different than that with his set theory, where he just basically created this whole thing really himself. And so it's kind of a unique thing that you can really point to a single individual who's really almost single-handedly responsible for the creation of this area of mathematics. And then set theory, of course, then eventually took off and has become an important part of mathematics. Uh, if you take a course like our students take one in discrete mathematics, they definitely do some work with proving some things about sets. Well, let's talk about number theory just a little bit. If we back up a little bit to the previous century, the 18th century, Euler proved Fermat's last theorem for n equals 3 and 4. And in other words, there's no natural number solution to x, y, z to x cubed plus y cubed equals z cubed, nor are there to x to the fourth plus y to the fourth plus z to the fourth. So he had that solved for that. Fermat's last theorem says that x to the n plus y to the n plus z to the n has no solutions that are integer solutions x, y, and z for any um, n bigger than, well, 3 and up. Okay. Euler introduced the idea of integers modulo n. Now remember, of course, Fermat didn't actually prove the last theorem, or well, he said he did, but that proof has never been found. Mathematicians now don't really think that he actually proved that. But some progress had been made on that in the 18th century. Euler had introduced the idea of integers modulo n. He proved that integers mod n are what we would now call a ring, and this work was foundational, leading to the eventual development of the concept of a ring and also of a group. Work was done on sigma of n, the number of factors of n, and phi of n, the number of numbers less than n that are relatively prime to n. Euler found several results related to quadratic reciprocity. P is a quadratic residue of q if x squared is congruent to p mod q, if that has a solution. So some of the work was done on this, a lot of it by Euler in the previous century, and some work was done in advancing those areas in the 19th century. Carl Gauss, who we've talked about previously, is one of the greatest mathematicians of all times. He only published about a dozen publications, but everything he published, all dozen works or whatever, are rank among some of the best mathematics that's been ever published and some of the most influential. His motto was few but ripe, so he would only publish what he thought was really significant and really polished. One of the first things, of course, was his dissertation in 1799, which included the proof of the fundamental theorem of algebra. A couple years later, the first year of the 19th century, 1801, he published a book that the English translation would be Investigations in Algebra. It's in it, he talks about integers mod n, quadratic residues, quadratic reciprocity. So he's extending some of these ideas that Euler had, greatly extending these ideas. And these form the foundation of a lot of, especially number theory, is a lot of it goes back to the work of Gauss. One of the people that Gauss worked with, interesting enough, was a woman by the name of Sophie Germain. She was born in 1776 and died in 1831 in France. And women were not generally encouraged to do mathematics, in fact, even actively discouraged to do mathematics. And so she corresponded with various people under the name of Monsieur Leblanc, and she did that to hide her gender, pretended she was a man in her um, correspondence. And Lagrange was a supporter, and her most important correspondence was with Gauss, and she did some advanced work on Fermat's last theorem. It's interesting that uh, during this time it was a time of the French Revolution, the Napoleonic period, um, and so she had found out that that the French were going to uh, invade Germany. She had heard the story about Archimedes being killed by the Roman soldiers coming in. She didn't want the same thing to happen to Gauss, so she tried to warn Gauss about this. In the process, she revealed that she was a woman to Gauss. Gauss was even more impressed with her work when he found out she was a woman, and they continued their uh, correspondence. And of course, Gauss was not killed in that invasion. Next, I want to bring forward a couple of people here. I as I pointed out, a lot of these folks that are become very famous mathematicians this time period didn't necessarily live long lives. Some of them did, but I want to bring up two mathematicians now that lived very short lives but made very big impacts in mathematics. If you had to say, well, who are the best mathematicians of all times? Well, if you measure it by the amount of time that they did work and how small that was and how important it was, both Abel and Galois, which are the two mathematicians I want to talk about next, would definitely rank way up there because what they did in a very short period of time is quite amazing. So Niels Heinrich Abel was born in 1802, died in 1829 in Norway. And Abel grew up very poor in Norway. Norway was in the midst of a conflict between multiple nations, including Britain and Napoleonic France, uh, and then also with other countries at the time. So at that point, Norway was part of Denmark. Then it became part of Sweden, and they tried to make a bid for independence. And there's a lot of upheaval going on in Abel's pretty short life there. And so economic conditions were not good in Norway, and his family in particular was not very well off. Um, at about age 15, he began to study mathematics seriously. In 1824, at the age of 22, he was the first to prove that it's impossible to have a general formula for solving polynomial equations of degree 5 or larger. Now, if you remember, one of the main thrust of algebra from way back, even even before what we would actually call algebra today was created by the Muslim mathematicians of the Middle Ages. A lot of that focus was on finding solutions of polynomial equations. Linear equations were almost immediately solved once people thought of it that way. Quadratic equations, at least some solutions go way back. Um, but if you remember, it was not until the Renaissance that a big push was done for solving cubic and quartic equations, and that was finally taken care of. So we found that there are general solutions to solving those equations, but uh, things had kind of stalled out for solving fifth degree and higher. And of course, there's a reason for that. It's because it's actually impossible to find a general solution built up out of abstract multi-divide powers and roots, the kinds of things you would write in like the quadratic formula and so forth, or the cubic formula. And so Abel was actually able to use some things that we would now call abstract algebra to show that these polynomial equations of degree 5 or larger, it's impossible to do that. And later he did some work which was unpublished on which polynomial equations could be solved by radicals, and that work was actually worked out by Galois, who we're going to talk about in the next slide. Um, This work was kind of revolutionary. It took a while to get others to recognize his work. He also worked on elliptical integrals, greatly expanding Euler's earlier work on that subject. We honor him by calling commutative groups abelian groups in his honor, although usually I see abelian groups written in lowercase a, which it should be uppercase since it's basically his name. Other folks get their name capitalized, but abelian groups are such a fundamental uh, type of groups that we just put as a lowercase a. He died at a very young age, at 27, from an illness. So think about all the fantastic things that he did, and they were basically accomplished from, well, he started studying mathematics at 15. He died at 27. He only had 12 years to do work. Most of that, and the first few of that was basically figuring out uh, what was going on. So basically, from 22 to 27, or from let's say 20 to 27, he did most of his work. So a very short period of working on mathematics, and yet was able to accomplish some things that people had been unable to do for many years, um, and made some significant progress there. He was friends with Jacobi, and they did some work together. And there was a Paris Academy had a contest. This is a typical thing that they did. They would have a contest and give prizes for the winners of these mathematical contests that were prestigious. They often led to folks getting university appointments after that. And Abel and Jacobi won one just after he died. That was a posthumous award. So amazing thing, one of the founders of some abstract algebra. Another mathematician who was doing similar work to Abel was Galois. He was born in 1811 and died in 1832. So 1811 to 1832, 1802 to 1829. So he was a little bit younger, 9 years younger than Abel, and died uh, just a couple years after Abel did. In 1827, he enrolled in his first mathematics course. Um, this guy has the most incredible hard luck story that you could imagine. He twice failed to get accepted at École Polytechnique, which was the premier school, certainly in France, one of the premier schools in all of the world at that time for studying mathematics. This is during the period of the French Revolution. So at that time, you had a lot of great mathematicians teaching there, like Lagrange, for example. The first time he tried to get accepted, he probably just hadn't studied enough mathematics to get that. But in 1829, he published his first paper on continued fractions. But his father had committed suicide in 1829, and right after that's when he tried to take his second entrance exam at École Polytechnique, and he failed that, possibly because he was so emotionally distraught from his father's suicide. So he decided he would switch gears. He was accepted at École Normale, which is a teaching school, but he got involved in some politics there and didn't pay attention to his studies. He was later expelled. He was destitute, but he started working on polynomials of higher degree and working on some things there. And so he had worked on some polynomial equations that he'd sent to Cauchy, but then he found out that Abel had already published uh, his work on the unsolvability of the fifth degree polynomial. Um, Galois probably independently figured out that as well. So when he found out about Abel's work, of course, he didn't try to get that published anymore. He then sent a paper to a referee to maybe get it published. But the referee, who was a pretty good mathematician, but couldn't understand it, sent it back. Abel Galois was extremely brilliant and very revolutionary in some of the in original and in the work that he did, but he was not necessarily good at communicating his work. And so due to the fact that he wasn't good in explaining himself, number one, and number two, that his ideas were so revolutionary, so he had a paper basically just got rejected. Then he made further progress and sent the work to Fourier. Figured, okay, well, Fourier will be able to understand it. Well, Fourier ended up dying without reading it. The paper was set unopened on Fourier's desk when he died. I mean, this guy can't catch a break. He sent some of his work for a prize, but it wasn't even considered. That was the prize that was given to Jacobi and to Abel, where Abel got it posthumously for their work. Of course, Abel and Jacobi deserved it, but again, there was another chance to get his work recognized. No avail. He also got involved in the politics of the revolution. He was on the side of the revolutionists, but at one point then the monarchy was reestablished. He was arrested twice and jailed once, eventually got out of jail, and then there was a dispute over a girl. And we don't know for sure if the politics had anything to do with it. It was probably just a romantic thing, but there was a fight, and there was a scheduled duel for the next day over this girl. Perhaps maybe some politics involved with this too, but the dispute over a girl mainly. And he wrote down some of his work that night before. A lot of it he'd already written down, but he ended up taking more notes and wrote it down, gave it to his friend uh, Louisville, and he went out for the duel the next day, and was killed at the age of 20. Now, if you look at this, basically, he was able, from the time he was about 16, 17 to age 20, so about 4 years, okay, he was able to get an amazing amount of work done. Louisville eventually published the papers of Galois posthumously in 1846, 14 years after his death. And even then, it took a little while for people to figure out what he was talking about. But he was extremely original and brilliant. He didn't communicate his work well as he could have, but mathematicians today were not always quick to understand his ideas. But eventually, once they were understood, his Galois theory is an important area of abstract algebra that connects group theory with ring theory. He was also very influential in the foundations of group theory. He was one of the first ones to give a definition of an abstract group. And Galois theory is used to determine which equations will permit solutions by radicals. It can also prove that there are no general fifth degree and higher formulas. And in fact, it's his approach that is typically used to show that proof. So in just 4 years of working on mathematics, Galois was able to create very innovative work that ultimately transformed the way uh, abstract algebra and mathematics in general, the way we work at that. So the way we look at those is changed drastically by his way of thinking. So, it's making me think about if these guys, Abel and Galois, had lived longer, had a little bit better economic situation where they could have spent even more time thinking about these, perhaps if they'd even collaborated with each other, how much could they have accomplished? It may have been tremendous. What they did in their very short lives was tremendous, even though it didn't last. They neither one lived very long. So one of the big things that happened in the 19th century was the birth of group theory. Now there were some precursors to group theory. Some went back a little bit further than the 19th century. One was the desire to solve polynomial equations of degree larger than 4, and that helped to lead to the definition of an abstract group, and it led to the study of permutations. So those things were involved there, and like I said already, that um, Galois was one of the first ones to define a group, and that was because of his study of solving equations. Lagrange was the first to systematically study the group of permutations, and permutation groups are a big important part of group theory. Abel and Cauchy continued the study of permutations. Euler and Gauss studied modular arithmetic, which is tied in with group theory. And the discovery of non-Euclidean geometries, which we'll talk about here in another video pretty soon in this playlist, also led to group concepts. So what's a group? A group is a level of abstraction of the idea of and a generalization of the operation of addition in the integers. So if we have a set with a binary operation, we'll call it star, that's on G cross G to G. So what does that mean? What's a binary operation? That means if you take two elements in G and you apply this operation, G star G, G1 star G2, you end up with another element in G. So it's closed under that operation. And such that, well, there exists an element which we're going to call 1 in G, so that 1 operate on A and A operate 1 is A for every A in G. So that's an identity element. And for any A in G, there exists an inverse, A inverse in G. Let me fix some things here. Okay, now the notation is a little better. So this is operation that's closed in G. There's an identity element, which I'm going to just call 1, so that when you say 1, say times A plus A times 1, A1 operate A operate 1, whatever that operation is, that you get back to A again. A retains its identity when you operate on it from either side by this element 1 for every A and G. Also, for every A and G, every element, there exists a corresponding inverse element, which I'm going to denote A superscript -1. That's A inverse. It's in G. So that A operate A inverse or A inverse operate A is the identity element 1. And then finally, the third one is for any A, B, and C in G, A operate B in parentheses done first, then operate on C is the same as taking B operate C and then do A operate on that. That's a commutative associative property. There's not, however, necessarily a commutative property. So these are properties that, say, addition or multiplication have with natural numbers. Well, actually, addition has with integers. Okay. And multiplication almost has these with non-zero. Well, multiplication has this with non-zero real numbers or rational numbers. Okay. So a group then becomes this abstract thing that we've set up here, where we generalize the like numbers or like the things in G, but not just necessarily real numbers or natural numbers or integers or so forth, but it could be some other thing that acts kind of like numbers. You have this operation, think addition or multiplication, but not necessarily just those operations, some more general things. So we're going abstract. We're generalizing the algebraic structure here. So this sort of gives us a set of axioms that define this particular thing. Okay, so Cauchy, Galois, and Cayley are considered the founders of group theory. Group theory becomes a very important area of research starting really in a little bit before, but mainly in the 19th century and then on till today. The formal definition of a group first appears in 1854 in a paper by Arthur Cayley. An earlier version of a definition of group was by Galois. Again, groups are an abstract generalization of operations. Many things turn out to be groups, including permutations that were studied by Lagrange, invertible matrices with matrix multiplication, which are studied by others, and many other things. So it turns out that some of these different things that have been studied, people realize that, oh, these kind of all have something in common. And they have something in common with things that we've known about for a long time, integers. And so, okay, let's take those things and let's say if we can prove something about these, say, groups in general, then that applies to all groups in all contexts. And then, of course, different kinds of groups that you study more about. Other groups appear in the study of geometry, for example, in symmetries of regular polygons, for example, and also in number theory. So a lot of these different things come about. And probably nobody did more for developing the basis of abstract algebra than Arthur Cayley. In 1821, he was born. He died in 1895. Much longer life than, say, Abel and Galois. He lived in England. He actually grew up in Russia for the first 7 years of his life. His family was English, but they were working in Russia, would kind of come home to England in the summer. He was born in one of those summers in England, but mainly spent most of his first 7 years in Russia. But then they ended up moving back to England permanently. He entered King's College School at 14. That was a couple years ahead of what most people would do. He entered Trinity College as a student in 1838. In 1846, he needed to get a career, so he decided to train for the law, and he became a lawyer. So he made his money as a lawyer, but ended up publishing over 900 papers. A lot of the things were on things like algebraic curves and surfaces, elliptical functions. He did a lot of early work on determinants and matrices and leading to linear algebra. He worked on invariant theory with Joseph Sylvester. He worked in non-Euclidean and n-dimensional geometry. And as I've said, he was one of the founders of group theory. And he's the first one to give a definition. He did what we sometimes now call Cayley tables, which are just basically operation tables, where especially if it's a finite group, you can list all of the elements out in a column and a row, and then do their product in the middle. It's just like multiplication tables for, that you did maybe learn in elementary school for multiplying out natural numbers. He did the same thing for different groups, and those are now named in his honor. They're called Cayley tables. He was the first one to really write out tables like that, just showing all the operations. He recognized that permutations, symmetries of polygons, matrices, Hamilton's quaternions that we're going to talk about in the next slide, that they were actually all had these characteristics in common that he called a group. And he's probably most responsible for getting group theory and abstract algebra in general going. I want to talk a little bit about Hamilton, William Rowan Hamilton. He was born in 1805 and died in 1865 in Ireland. He started studying mathematics at age 13. He was good enough that he was able to found an error in the work of Laplace at 17. He entered Trinity College, Dublin, in 18 and achieved a distinction for his studies that was only awarded once in about every 20 years. Some tragedy here. He fell in love with a young lady, but ultimately her parents arranged for her to be wed to someone else, a guy that was 15 years older than him. He wrote a lot of poetry. He was especially when he was depressed. And at 1827, at the age of 21, he became a professor of astronomy at Trinity College. He did some important work in optics and dynamics. In fact, probably in some ways his best work was in optics and dynamics, but he was more interested in mathematics than astronomy. And he was trying to work with complex numbers. He treated them as ordered pairs of real numbers, and he was trying to apply some physical phenomena to try to explain, three-dimensional stuff. He was trying to figure out how to do that. And in 1843, he discovered or invented the quaternions, which was the first non-commutative algebra. It's actually a non-commutative division algebra. So to tell you just a little bit about what quaternions are, a quaternion group is a group of order 8. The elements of it are 1, -1, I, -I, j, -j, k, and -k, with some relationships that I squared, j squared, and k squared, and I times j times k are all -1. So I times j is k, and so forth. So one of the ways you'd be familiar with I, j, and k now, if you've taken a course such as Calculus 3, Vector Calculus, or perhaps a course in linear algebra, or something with vectors, you can think of I, j, and k as the standard unit vectors, and the multiplication of these particular numbers was like what we would now call a cross product. Now, Hamilton's work predates vectors and a cross product, but squaring all of them was -1. And this turns out to be a group, and it's in fact the smallest non-abelian group. Meaning it's not commutative. So for example, I times j is k, but j times I is -k. Okay. Now the quaternions that he was studying was then taking these sort of as generators and doing linear combinations of them. So the quaternions were the set of numbers, if you want to call them set of things, of the form a plus bi plus cj plus dk, where a, b, c, and d are real numbers. So there are 4 of those numbers, a, b, c, and d, hence quattro or quaternions for 4, basically ordered 4 tuples. And then from the time that in 1843 when he invented quaternions, he basically spent the entire rest of his life studying these quaternions that he invented. He ended writing as much as like an 800-page, approximately page book on quaternions. But the quaternions were important. Not only are they good examples of groups and led to some things in abstract algebra, they're also precursors to development of vectors. Some later mathematicians have realized that we didn't need the full theorem of quaternions, that you could get what you really needed with essentially cross product, dot product, and a scalar multiple. And so this the idea of linear algebra and vectors and vector operations came out of that work, with other people working on it after that. Another mathematician I want to mention is George Boole. He was born in 1815, died in 1864 in England, and he did a lot of work with logic, and his idea was to reduce logic to some simple algebraic techniques and to incorporate logic into mathematics. This led to what we now call Boolean algebra, and it is applied to modern day computer science. So Boolean algebra is extremely important in understanding how programming works and how computer science works. He also did some work on differential equations, calculus of finite differences, and probability. And now I just want to quickly mention a whole bunch of other mathematicians and not say a lot about them, but just there's so many important mathematicians of this century, and here are a few that did some important work in abstract algebra or in algebra in general. George Peacock from 1791 to 1858 lived in England. He did work on the logical foundation for algebra. Carl Jacobi, 1804 to 1851 in Germany, did work on elliptical functions, partial differential equations, and dynamics. Augustus de Morgan lived from 1806 to 1871. He was English. He worked in mathematical logic. Uh, Eduard Kumar from 1810 to 1893. He was born in Poland, lived in Poland and Germany. He came up with the concept of an ideal, and that led to the idea of an integral domain and rings, so sort of a precursor to ring theory. James Joseph Sylvester from 1814 to 1897 in England did work with matrix theory, so that led to matrices, linear algebra. Leopold Kronecker lived from 1823 to 1891 in Poland and Germany. He did work on the theory of equations, elliptic functions, and algebraic numbers. Gotthold Eisenstein lived from 1823 to 1852. He was German. He did work on quadratic and cubic forms, reciprocity, and number theory. Charles Dodson lived from 1832 to 1898 in England. He did a lot of important work on logic, but he's probably best known, not probably, absolutely best known as an author where he used the pen name Lewis Carroll. Lewis Carroll, Charles Dodson, wrote the Alice books, Alice in Wonderland and Through a Looking Glass. And by the way, those books have some interesting logic and things, mathematics actually in the books, even though they're very whimsical. John Venn lived from 1838 to 18. Something's wrong there. Let me look up his dates. So the 1834 was right, but it should have said 1923. He had a long life there in England. You probably know of him from his Venn diagrams and some of the work that he did with set theory. Another one I'll mention is Emile Mathieu. He lived from 1835 to 1890 in France, and he did some work with group theory. He found 5 simple groups that are part of the list of sporadic groups, and they're called the Mathieu groups in his honor. Camille Jordan, from 1838 to 1922 was his life. He lived in France. He did work in algebra, particularly in group theory and Galois theory. Skipping down, Otto Holder lived from 1859 to 1937 in Germany. He also did group theory and Fourier analysis. There is a Jordan-Holder theorem that is extremely important in working with factor groups in group theory. That's those two guys. And another guy that was really important is Sophus Lie. He lived from 1842 to 1899 in Norway, and now Lie groups and Lie algebra are named after him. He also did work in differential equations, so he did a lot of work on this important areas. Lie groups and Lie algebras are definitely whole areas that are studied to this day. So there are a bunch of really important algebraists. Each one of these guys probably deserves a whole video himself, but we're going to call it there and move on to looking at some geometry in the next video.